So we left off talking about curl, which was something which is a topic or an object specific to vector fields in R3. So in 3 dimensions, higher or lower, you can't really do much. Though we're going to talk a little bit about what in 2 dimensions, how we could kind of fake something kind of like a curl. And we talked about the physical interpretation. I had my Rubik's Cube out, and if we're acting on this with a vector field, then it's going to have some spin to it. And so the axis of spinning and the magnitude of spinning tells you everything you need to know about how it's spinning. Okay. Cool. And so we started practicing some computations. So we had this vector field, and we said, hey, like the things don't really spin when you put them in this vector field. But now we have this next vector field. And so we're going to see, okay, what happens to this as we, what kind of spin do we get when we put, what kind of curl do we get when we put something in this vector field? Okay. Cool. So let's go ahead and do this. So we have I, J, K, ddx, ddy, and ddz. And then we have negative y, x, and z. And so what we get is right. So this time I won't write all of this out, but I'll just kind of say, okay, so we're looking at the I component. So it's, we're ignoring this. So it's ddy of z, so 0, minus ddz of x, 0. So far it's looking similar to what we had over here, minus your j component. So now we're deleting this row or this column here, and we can do ddx of z. So again, that's 0 minus 0. So the ij component is looking very similar. But lastly, in the k component, it's where things get interesting. So if we delete this, now suddenly we actually have some derivative here. So we have the derivative of x with respect to x, that's 1, and then minus the derivative of y with respect to, or the derivative of negative y with respect to y. So minus negative 1. And so we get, this is going to be, giving us some kind of spin just in this component. So we get 2 times the vector k, which means that you just kind of, if you're thinking in 3 dimensions, is your xy plane is here, and then your z-axis is like this. That's just a vector pointed straight up of magnitude 2, right? So we just have a vector pointed straight up, which means that if I put something in this vector field, if we're living in 3-dimensional space and you have, xy plane here, however you want to orient that, and then your z-axis is pointed straight up. If I put something in here, it's going to spin counterclockwise, and 2 determines the speed. There are different ways to interpret that in terms of like how exactly that 2 relates to the speed at which it's spinning. But the positive tells us that from the, you can use a right-hand rule. So if it's positive, then you point in that direction. If it's negative, you point in that direction, and this tells you the direction of that it's spinning in. Okay, so in this case, it'll spin counterclockwise if you're looking at it from the top. Okay, so that's kind of gonna be how it spins. Perfect, the axis of symmetry is just perfectly straight up, and then by the right-hand rule, it's spinning counterclockwise like this. So if you put something in here, it's just gonna spin like this. Okay, cool. Any questions on that? Okay. So I like to explain conceptually what's happening, but also just, in terms of the arithmetic, nothing too crazy ever happens here, right? Just going to take some partials and yeah, and then just like add things together. So someone's asking if positive k is clockwise. So not positive k. It's a little more complicated than that. So basically, you're gonna have to use the right-hand rule. So you're basically point your thumb in whatever direction that vector is pointing in. Okay. So if that vector is pointing over here, then I use that as my axis, and then I use the right-hand rule to tell me, okay, so that means it's spinning in this direction, okay? But if I'd gotten the negative of that vector, my thumb would be pointing the opposite way. So it's still spinning on the same axis, but now it's spinning in the opposite direction, right? So if I instead of 2k here, I had negative 2k, my thumb would be pointed down, and so it would still be spinning just like this, but it would be spinning this way instead of this way. So this way instead of this way. Okay. Good question. Yeah. Okay. Let's see. So that's curl. And then we can use, so the curl only happens in 3 dimensions, which is nice because we live in 3 dimensions, and so we could visualize it really relatively easily. But it's not nice because that means it's slightly less useful because you don't have as many applications for it. You can't apply it in other dimensions. But it turns out you can do something in 2 dimensions that kind of replicates what it does in 3 dimensions. So what you can do is define something called the scalar curl. So if you have a vector field in R2 now, so notice that F is a vector field in R2, then we can define the scalar curl, okay, of F, okay? And this is give me one sec, I had it written down. I want to make sure I get it in the right order. Okay. Yeah, it's df1 dy minus df2 dx. Okay. So we use the same notation, but it's just the context, right? So if we're plugging in a vector in R2, then we use the scalar curl. If we're plugging in a vector in R3, then we use the other curl that we were talking about. You can call it vector curl if you want, but no one really calls it that. Okay. And there's an explanation here for why we can do this. So basically what we're saying is we can just think of this. If we have a vector field in R2, which we could think of as all like the drawings I would draw vector fields in the last section, right? Like those kind of, they're just flat. What you can do is you can say the vector field is going to be exactly that vector field, but with nothing in the k component. You could just put nothing in the k component, so 0 in the k component. Now it's a vector field in R3, but that is, it's just basically stacks of that vector field for every value of z. And so the vectors never move in any z direction, they're always just perfectly flat. And so what that means is that if you have any spin, it's always going to be either, the axis is going to be perfectly straight up, okay? Because, right, so you're taking these flat vector fields and you're stacking them on top of each other. So none of the vectors are pointed at all in the z direction. So there's never going to be any spin with any component in the z direction. So the spin is always going to be, the axis of spin is always going to be perfectly straight up. And so you're just going to spin kind of, perfectly straight up, either clockwise or counterclockwise. And so what the scalar field is doing is it's just taking the magnitude of the curl in that direction, because the curl is always going to be either pointed straight up or straight down. And so just take the magnitude of that vector. So here I'll show it off a little bit more, but we can say something like the curl of F. Again, if you set it up this way, the curl of F is, the df2 dz minus df3 dz or dy. But in this case, f3 is just 0, so d0, and that's going to be your I component plus or minus df3, or d0 d x minus df1 dz. That's your j component. And then your k component is going to look familiar. df1 dy minus df2 dx. That's your k component. And what you're going to notice is that, so this is 0 and this is 0 for sure. But because our f1 and f2 are coming from vector fields in R2, f1 and f2 don't depend on z. In other words, there's never going to be a z in that part of the formula. And so this becomes 0, this becomes 0, and so all of this becomes 0. And so you just get df1 dy minus df2 dx times k. And then what we do, and then because no matter what we do, if we start with a vector field in R2 and pretend it's a vector field in R3 in this way, you always just get the k component. We just say, well, if it's always just the k component, that should just take the length of that to be our scalar field. So we just take the coefficient in front of the k. And that's where we get this formula here. Okay. Okay. So what you can imagine is a vector field in R2. So if like you just have the flat vector field, you put something in it, another flat object, maybe like a square. You could think like a piece of paper. Remember, it's not coming out at all in the third dimension. So it'll start spinning like this. So what this is doing, what this number is doing, is it's just telling you how fast it's spinning and whether it's been, and then the positive or negative is telling you either clockwise or counterclockwise. Okay. Cool. So let's see. I think I have some examples here prepped for us. Yeah. Cool. So we have this vector field here, xy, and then this other vector field here, negative xy. Vector fields, again, that we've seen before. Okay, so let's start with this one. So I'm going to write curl of f. Now, in the homework or a well-written problem, we'll always say compute the scalar curl when they want you to compute the scalar curl, and compute the curl when they want you to compute the regular curl. That being said, you can tell which one they want you to do because this is a vector field in R2, so they have to be asking for the scalar curl, right? There's no regular curl for vectors in R2, or vector fields in R2. You need to have, you need to do the scalar curl if you're in R2. Remember, the curl is for R3, scalar curl is for R2. I'm going to outline that all a little bit after this problem, after these examples here, probably. So we do this, and this is again just d f1 dy minus df2 dx. The order of this is important just because it gives you the right sign, positive or negative. And so in this case, we take this, the derivative of this with respect to y, which is 0 minus 0. So in this case, we get 0, which again makes sense. So now I can actually draw things because it's actually in 2 dimensions. And so this, remember, this vector field looks like this, right? I've brought up this vector field enough that hopefully we all kind of remember what it looks like. And so, and then as you get out, they get longer. Oops. Okay. So you have a vector field like this. Basically, if I were to put a rigid body in here, it actually helps to think of it as like a perfectly spherical rigid body. Then basically the force you're putting on this side of the body is the same as you're putting in the force of this side of it. And so it's kind of at a sort of equilibrium. So it's never gonna spin at all if you put something here. Okay. So that's kind of what's going on in this picture. Okay, that's why we get a 0 here. Let's see this next one. So this next one, we kind of have a picture of 2. Maybe I'll draw the vector field before we do that. Someone's asking a good question in the chat. Someone's asking, for computing the vector field, is there anything else that, or the curl, are we usually expected to do something else, or is it just kind of compute the curl and move on? Depends on the problem. I think looking at the homework, I think most of the ones on the homework were just kind of compute this curl and move on. But we'll see. Actually, I should on the homework, I think that's true, but we're going to see in the next slide that you can do other things. I mean, the curl gives you a vector field, so then you could theoretically do anything you can do to a vector field, you can do it to the curl of a vector field, and so we can do more too. Okay, so this is not great scale, but gonna get in the picture, right? So it's these big. Oops. Okay. So the point is, it's something like this. So this one we're going to expect to have some curl, right? Because if we drop a rigid body in here, right? If we drop a rigid body in here, the forces out here are going to be stronger than the forces out here. So it's going to start spinning. It's going to start spinning in this direction, right? Okay. So let's start computing it. So we take the curl of F, and so we take dF1 dy minus dF2 dx. So in this case, we get something interesting. So we get this case, we get df1 with respect to y, which is -1 plus the derivative with respect to x of this guy, or minus 1. So we get -2. Yeah. So the fact that it's negative, yeah, it feels like it should be going the other way. If it's negative, did I do this? No, that's right. Oh no, I think I might have my formula backwards actually. Yeah, because you'd just be looking at the k component. Let me go back here. Yeah, so it should be this. Oh, my formula is backwards. Okay. Glad I caught that eventually. I wish I would have caught it sooner though. So yeah, so a good chunk of, so this is backwards. So it should be df2 dx1, or dx minus df1 dy, right? So it should be, because it's coming from this part of the formula. So, and I had it backwards here as well. So df2 dx and then df1 dy. Okay, so that's why this should be the other way. So it should be plus and then a minus here. So that gives me plus and plus +2. That makes sense. Okay, so let me regroup and show you what went wrong there. I messed up my formula when I wrote it down initially. It's because I made a mistake in when I was writing this up ahead of time, my reference sheet here. And it should come from this formula, which comes from taking the determinant. Okay, so just if you don't want to make the same mistake I did, then you should just, this formula is always going to come from this determinant. You'd always do x, y, z, and then 1, 2, 3. That's, those are always in the same order. So then you just take the determinant. So then you look at the k coordinate specifically, and it should be ddx of f2 and ddy of f1. So it should be this minus this, and so it should look like this. And so that's what your scalar curl should look like. And I got mine backwards. And I specifically mentioned that the order is important because if you get it backwards, you're going to get the wrong sign, which is exactly what I did. It's the exact mistake I made. So you should be in this order. And if you have doubts about this order, you don't have to just memorize it like I tried to do. You can always just recoup it from this determinant. Just what's the k component? Just this and this. It's this minus this. So keep that in mind. Don't make the same mistakes I did. Be better than me. And so that is why we got a positive number here. So the way I caught it was, so you should think that positive means counterclockwise and negative means clockwise. And so I saw a negative number here, but I could tell from the picture that it should be moving counterclockwise because there's stronger forces out here than there is in here. And so it should be moving this way. And so I knew that there was going to be a problem, that was a problem there. And so I was able to remedy that with this by fixing the formula. So yeah, this would also be the other way, but doesn't change the answer here. Okay, cool. Sorry about that little mistake, but hopefully that was a learning experience for everyone too. Again, you don't have to blindly memorize like I tried to do. Just when in doubt, use the definition of the determinant. And then the way you can catch yourself is by remembering that it's not always this easy because you might not always have a nice picture of the vector field, but a positive scalar curl should be counterclockwise and the negative scalar curl should be clockwise. Okay. The reason for that is that basically when we picture the XY plane, we want to picture the positive z-axis pointing toward us and the negative z-axis pointing away from us. So by the right-hand rule, if we get positive here, then that means it has positive z component. So you're kind of pointing. So if this was your screen and you lay it down, then it's pointing this way, and so you're kind of looking like this. And by the right-hand rule, that means we're going counterclockwise if it's positive, and clockwise if it's negative. Okay. Hopefully all my hand gestures are at least a little bit helpful. Okay, cool. Cool, any other questions? Okay, so a couple of more concepts I want to get to, but I think first I want to kind of outline a little bit of the three objects we've discussed so far. So we've talked about divergence, we've talked about curl, and we've talked about scalar curl. Okay. And I want to kind of compare and contrast each of these. Okay. So we could kind of have some idea of what, so we know, so we don't get them confused. We make sure that we're using the right formulas and stuff like that. So, so the divergence works in any dimension. So works in any dimension. Curl is only in R3. And then scalar curl is only in R2. Okay. Okay. Now for all of these, what they need is a vector field. So you need to be given a vector field. So you need to start with a vector field. And so that's all of these. Okay. And now, but they all start with the same thing. So you're given a vector field and you have these three objects, but what you end up with is different depending on which formula you're using. So if you're doing divergence, you're going to end up with a scalar field, which is just a number, but it might depend on all the variables. It can depend on all the variables. The curl is you end up with a vector field. So it's a vector valued function in as many variables. And the scalar curl, you also end up with a scalar field. Okay. These are the big differences. I think there's one more. Maybe you can write like the physical interpretation here, but I think maybe I guess I could write it. So this determines the expansion and compression of the vector field. That's what the divergence does. The curl determines the axis and velocity of spin of an object in the vector field. Okay, and then the scalar curl, this just doesn't determine the axis because it's in 2 dimensions, so the axis can only possibly be straight out at you, and so determines the velocity of spin of an object in the vector field. Okay. That's it. That's your definition. These are kind of your compare and contrast. So if you want to, this is a good reference for like making sure you kind of understand the differences between them. Okay, cool. Any questions? Okay. Here, when I say velocity in these 2 definitions, am I talking about angular velocity? Yeah, so if you're familiar with the concept of angular velocity from physics or from wherever, basically it's, right, so velocity is the concept of speed, but with direction. And so in terms of angular velocity, all that means is speed in terms of like a radians per minute or something like that, in terms of, you know, how many rotations it's making in a fixed amount of time. And the velocity, the direction part of it is just whether it's going clockwise or counterclockwise. And so that's kind of what velocity means in terms of the curl and the scalar curl. So it just means, is it spinning slowly or is it spinning really fast? And is it spinning clockwise or is it spinning anti-clockwise, counterclockwise? Okay. So that's all that means. Cool. So with that, we can move on to the next little part of this, the last couple of little things. So these, they're not, I don't think there are any homework problems on this, but it's something that you should know kind of moving forward, and you should have written down as a reference in your notes, because basically what this is saying is, so you start with just some kind of scalar valued function, then you take its gradient, and what we discussed yesterday, is that if you take the gradient of a function like this, you get a vector field, right? So you can always you can start with the function, take its gradient, and we think of that gradient as a vector, but it's actually a vector at each point because it depends on the point, right? It depends where you are, what the gradient is going to depend on where you are. And so what that means is that it's a vector field. And so you have this vector field. You can take the curl of it, right? If you have a three-dimensional vector field, it's in 3 dimensions, so you can take its curl. And so what happens if you take the curl of a gradient field? Well, in this case, it turns out that you get 0 here, right? So your question is like, okay, why does this happen? Well, remember that the gradient of f is, so I'm calling this a proof. It's like a little mini proof. I don't think I've ever included a proof in class, but this one was nice, and it was, I think, approachable enough for us that I think I want to include it so that you can kind of at least see once what like kind of proving things looks like. So you have df dx, df dy, and df dz, right? That's what the gradient of a function is. So we laid out our definitions, and then the curl of a vector field is to then take the cross product of the gradient with a the cross product of your vector field with the gradient operator. And so all that means is you set up this formal derivative. So you have your I, your J, and your K, and you take ddx, ddy, ddz, and then in the bottom row, you just put whatever your vector field is. In this case, that's df dx, df dy, and df dz. And now some of you can already start to see, if you're really comfortable with the determinant, you can start to see what's happening here, what's about to happen. But if not, let's spell it out a little bit. So we start with the I component. Well, if we take the I component, we're ignoring this column and we're just doing this little mini determinant here. So it's ddy of df dz minus ddz of df dy. Maybe now you're starting to see what's happening. Well, let's keep going just in case. So then we take the j component, which is dx of df dz minus dy of ddz of df dx. And then last but not least, the k component. We just do this last one. So we get ddx of df dx minus ddy. Oh, sorry, this should be df dy, and then ddy of df dx. Okay, so we write all that down. And then what do we notice? If we take ddy of df dz, and then we take ddz of df dy, right? This is just my mixed partials. So I'll just rewrite this in a different notation so that we kind of can see what's going on. This is just fzy minus, let's make that clear, zy, and minus fyz. And then you have fzx minus fxz in your j. And then we have fyx minus xy. Remember, when you switch notations, the order switches. But what happens when we take these mixed partials? If I take, remember, f of yz is equal to, maybe I'll write it the other way, f of zy is equal to f of yz. Maybe that belongs down here somewhere. Belongs over here. Okay. So what does that mean? That means that this difference here, so if I subtract over, this is 0, right? Same thing with all of these. Because mixed partials are equal, I just get the 0 vector. So we call that done. Okay. So the reason that the curl of a gradient is always 0 is just the law of mixed partials. So if you can just do this, do the computation here, and you just get a bunch of mixed partials subtracted from each other. And since mixed partials are equal, then then you just get 0 in the end. Okay, that makes sense here? Okay, cool. So now let's move to the next concept. Next concept is similar. It's combining just different notions that we have from class. So this was the curl of, we had this in the last section. We learned that the gradients, that was like an important vector field that we often want to do, that we often want to use, and then its curl is kind of since we can take the curl of any vector field, in this case it ends up being 0. So someone's asking, why is this important? So I guess that's kind of a big question. Computationally, it's nice because maybe not in this class, but in some other class at some point, you might be computing some like curls of stuff, and that if the vector fields you're taking came from a gradient, then this is going to be a nice computational tool. So you don't have to compute, gradients every time. I think conceptually, it's maybe a little harder to explain, like what, why this is super interesting. But basically, if the curl is coming from some function, then you get. Yeah, I think maybe the more useful thing is in the opposite direction, in what we call in the fancy word for it is the contrapositive, which basically, whenever you have an if-then statement, you can flip it, but you have to negate everything. So basically, if you have a vector field and its curl isn't 0, then that vector field couldn't have come from a, yeah, I think this is worth writing down. So like, why is this important? So in particular, if the curl of some vector field is not 0, then f is not the gradient of any function. So yesterday we talked about integral curves, right? And before that, I kind of said, well, can we take, we can think of a vector field as like the derivative of some function, because you can get it from a gradient. The question was, can we move backwards? And this here kind of answers that question. We can't always move backwards. We can't always recoup a whole function from a vector field as it's via the gradient, because if the curl is not 0, then it can't have come from the gradient of some vector of some function. Okay, so that's kind of one interesting application to it. Okay, cool. Good questions. Maybe not the most satisfying answer, but it's just kind of a answer. Okay, the last one is it's a similar idea, kind of, where we kind of are always taking we're just kind of taking combinations of different concepts that we've talked about. But in this case, you have the divergence of the curl. So the curl, right, is right, you start with a vector field in R3, take its curl, that gives you a different vector field in R3. Okay, the question is, what is the divergence of that vector field? Okay, and then, again, this one, it turns out, is also going to be 0. And this one I won't prove, because the proof is not as straightforward. So I think it results, it comes from something very similar to what we had before. Just laws of mixed partials. But yeah, this one, if you're gonna ask why this one is important, I don't think I have as good of an answer for this one. Okay, but these are just some formulas. So part of my duty is to make sure that your notes at the end of the quarter are like relatively complete, and so that you can reference them, because someday you might be in some other class, right? And someone will say like, "Oh, this is just stuff you should have learned in multivariable calculus." And so even if you didn't like internalize this super deeply, you want to, and you go back and you reference your notes from this class, I want you to be able to say like, "Oh yeah, he did teach us that." Okay, and you don't resent me for the rest of your life. Okay.